Let's show that the function fx equal to x to the power 4 plus 3x plus 1 has exactly 1 0 in the interval -2, -1. We'll be using Intermediate Value Theorem, or in short IVT, and Rolle's theorem. First step, we apply Intermediate Value Theorem to show that fx equal to x to the power 4 plus 3x plus 1 has a 0 in the interval -2, -1. So we want to apply Intermediate Value Theorem. First step will show that in this case that f is continuous. Fx equal to x to the power 4 plus 3x plus 1 is a polynomial function. It is a polynomial function, and we know that polynomial functions are continuous throughout R. If the function is continuous throughout R, then it should be continuous on the closed interval -2, -1. Let's determine the value of f of -2 and f of -1. f of -2 equal to -2 to the power 4 plus 3 times -2 plus 1. That's equal to 16 minus 6 plus 1. That's equal to 11, which is positive quantity. How about f of -1? f of -1 equal to -1 to the power 4 plus 3 times -1 plus 1. That's equal to 1 minus 3 plus 1. That's equal to -1, negative quantity. Observe that f of -2 and f of -1, they are of opposite sign. By Intermediate Value Theorem, by Intermediate Value Theorem, by Intermediate Value Theorem, there exists a real number. There exists a real number x naught such that f of x naught equal to 0. f of x naught equal to 0. So x naught is a root of the polynomial equation. That is, x naught is a root. And again, by Intermediate Value Theorem, x naught must lie in the interval -2, -1. Okay, we got a root in this interval. Obvious question is, does there exist another root? The answer is no, and we need to prove it, and we will prove it using Rolle's theorem. You may ask, what's the significance of Intermediate Value Theorem? To understand it, we draw x-axis and y-axis. And we know that f of -2 is positive. f of -2 is positive. And further, we know that f of -1 is negative. f of -1 is negative. And we are given that the function is continuous. So let's draw a continuous curve. When we draw a continuous curve that passes through f of -2, which is positive, and f of -1, which is negative, somewhere we must come across a situation that f of x naught is exactly equal to 0. f of x naught is exactly equal to 0, and x naught must lie on the interval -2, -1. So that's what it's because of the continuity of the function, and the fact that f of -2 is positive and f of -1 is negative. It's because of the continuity of the function and the fact that they are of opposite sign. the function takes opposite sign at the endpoint, and that guarantees existence of a root. Next question is, if there is a 0 and we show that there is a 0 in the interval -2, -1, how many zeros does the function has? We apply Rolle's theorem to show that fx has exactly 1 0. Let's do it. We will apply Rolle's theorem. You see that f of -2 is negative, f of -2 is positive, and f of -1 is negative, and that's enough to say that there is a root. There is a 0. Now we need to show that there is exactly 1 0. Suppose, if possible, there are 2 zeros. Suppose, if possible, we will do it by contradiction. So we will assume that if possible, there are 2 different zeros. Those zeros should be different, right? If they are same, then we'll get same zeros. There are 2 different zeros, alpha and beta, such that obviously if they are the 0, then f alpha has to be 0, and f beta is also has to be equal to 0, and obviously alpha is not equal to beta. Now if alpha is not equal to beta, either alpha is greater than beta or alpha is less than beta. We assume that by simply interchanging, and we do not lose any generality, we assume without loss of generality that alpha is less than beta. Obviously alpha and beta, we are assuming that such root exists in the interval -2, -1. So alpha has to be greater than or equal to -2 and less than or equal to -1. Beta also has to be less than or equal to -1. Both has to be lying between -2 and -1. Okay, now we consider the interval alpha, beta. We consider f in the interval alpha, beta. Now, if we want to apply Rolle's theorem, we need to make sure 3 criteria are satisfied. We need to make sure 3 criteria are satisfied. 1, 2, 3. First one, f has to be continuous. Is this function continuous? Yes. F is a polynomial. Once again, it is a polynomial. So continuous throughout R. In particular, so continuous on the closed interval alpha, beta. If it is continuous throughout R, then it should be continuous in a smaller interval alpha, beta. Again, f is a polynomial, and so differentiable, you can differentiate any polynomial, and it is differentiable on open interval alpha, beta. It is differentiable throughout R. For every real number it is differentiable, so it should be differentiable in a smaller interval alpha, beta. Last point, f alpha equal to f beta, the value of the function at the end point must be equal. F alpha is equal to f alpha, equal to 0 is not necessary. So what's enough is f alpha equal to f beta. By Rolle's theorem, there exists a constant c. There exists a constant c such that by Rolle's theorem there exists a constant c such that f dash c is exactly equal to 0. F dash of c is exactly equal to 0, and that c has to be bigger than alpha, less than beta. how much is f dash c? But fx equal to, it is a polynomial function, so we can differentiate it, x to the power 4 plus 3x plus 1, and so f dash x equal to d dx of x to the power 4 plus 3x plus 1. If we differentiate x to the power 4, we get 4x cubed. It's a polynomial, so we can easily differentiate. If we differentiate 3x, we get 3, and then derivative of 1 is 0. So if it happens that f dash c equal to 0, if f dash c equal to 0, then 4c cubed plus 3 equal to 0. That is c cube equal to minus 3/4, that is c equal to minus of cube root of 3/4. However, c is greater than alpha and less than beta, and alpha beta are lying between -2 and -1. So mod c, as it lie between -2 and -1, must be greater than 1. Okay, since c is greater than -2 and less than -1, even it might be equal, or it cannot be equal either, by Rolle's theorem, that constant must lie in the open interval. So c is lying between -2 and -1, comma mod c is definitely greater than 1, but in this case we find that mod of c equal to mod of cube root of 3/4 is less than 1. So no such c exists. No such c exists, or our supposition is wrong. Our supposition is wrong, and we conclude there is exactly one root. We conclude that there is exactly one root. So there exist a 0 and only 1 0 of fx.